Hello, I am Felicia Horne. I attend Tuskegee University and I work under Dr. Rangari. He's my major professor. And this poster is on the synthesis of barium titanate iron oxide nanoparticles via 3D printed thin film composites. Um, so, multiferroics are just defined as materials that exhibit more than one of the primary ferroic properties in the actual same phase. So we're speaking to ferromagnetism as well as ferroelectricity. So the goal is to create multiferroic nanoparticles and at some point have multiferroic materials. So these nanoparticles were actually infused into a polymer, a two-part moldable silicone elastomer, part A and part B. So before we actually did that, the nanoparticles were synthesized. So the barium titanate was commercially purchased, and then the iron oxide nanoparticles were synthesized along with the barium titanate through iron acetate, urea, and DMF. And those were they were done through a sonochemical um, reaction for about 3 hours. And then from there, the particles went on to the centrifuge to be washed. And from there, once dry, we were able to get the particles. So from that, I was able to infuse the particles in this two-part moldable silicone, part A and part B. The ratio was for that polymer was 1-to-1. And the weight percent for the nanoparticles was 5 weight percent that we put into the polymer, which again, it was mechanically mixed. So we were able to get this polymer via a syringe, and I got 5 by 5 square inch samples to put on a hot plate via a high rare 3D printer in order to get these thin films. So from that, that's how we actually were able to fabricate this polymer, and then go on from there to get these characterizations of SEM, XRD, and of course optical. So with XRD, we wanted to ensure that there were the elements within this thin film that we said that we put in them. So we're looking for the barium titanate. We're looking for iron oxide as well. So if you can see for the XRD spectra, it shows we basically paired it up against a barium titanate spectra that was already in the system, and we have the exact same peak. So the barium titanate was again commercially purchased, so we know that's there, but we just wanted to still make sure that it was in that matrix. So also the iron oxide, you see the iron oxide peaks there as well. So we were able to find that out via XRD, and the same with SEM. If you see up top, we have image A and B. We were, looking for the barium titanate alone through line scanning through the EDEX SEM, and we were able to identify peaks for barium titanate. And then for image B, the same with the iron on that polymer matrix of the silicone. So that's just what that is. So we were able to identify that as well within that sample. Now, also with this thin film, we were able to do optical characterization, and which was the absorbance of the spectra, the absorbance for that thin film. And from that, we just found out that we indeed did have a 2.4 band gap, and that goes along with that iron oxide and that barium titanate within that silicone matrix of my polymer of that thin film. So again, with this work, we were able to characterize through SEM, XRD, and absorbance that multiferroic nanoparticle, the nanoparticles of barium titanate and iron oxide within that thin film composite. I just like to thank my advisor, Dr. Angari, UNL, and my funding agency, the NSF CREAM. Thank you.